In this video, we're going to look at partial derivatives for data as presented in a tabular format. Note that this is not a linear function. How do we know that? As we take steps of common y jumps, so y increasing by 0.1 and 0.1 and 0.1, we don't always see the same gap between the z values. Here we go up by about 2, whereas here we're going up by about 5. So it's not a linear function, but we should be able to get a slope out of this using the kinds of estimates we've done before. We're going to focus on the 0.11 and look for, or try to calculate, the partial derivative of f with respect to x out of that point. Well, the basic construction we're going to use is what we've used before. If we're talking about the rate of change of f with respect to x, that's approximately the change we see in f when we change x by a little bit, specifically increasing if it makes our life easier to think about. So the key thing is to note where the x values are changing, and that we see going from here to here. As we increase x from the point we're looking at, and we end up at the next point, we see a resulting change in the function going from 7.39 down to 5.99. And so we can capture that. And that looks like the end value for f minus the start value. That's how we calculate our changes. And then we can also contrast that or divide through that by the x end minus the x start. Or you can skip this step if that connection is clear to you. The final value for f is 5.99. Our initial was 7.39. And we divide through by 1.1 minus 1.0. Because the value of the function, the value in the table here, was going down, we fully expect the derivative to be negative, and that's in fact validated by what we get. When we cancel or subtract this out, we end up with negative 1.4 over 0.1, and that equals a slope of negative 14. That'll be an approximation because we only had one value here and not all the values in between. It's not exact, but it's a reasonable approximation. In exactly the same vein, we can approximate the partial derivative of f with respect to y by doing the same type of calculation. This time, though, I'll highlight the cells we're using in red. We will have the same starting point, but we'll compare to a point where x remains constant, but the y value has been changed. And so all the same structure here. We take the end point minus the start point. Those are the two f values, and then we compare it to the y values that we used as well. And if we do that subtraction, we get a positive value. Not surprisingly, because when we take this step in positive y, the z values go from 7 up to 9. And when we end up scaling that, we end up with 25.8. Again, that's an approximation of the slope we're looking for. Now, are those the only values we needed to use? Absolutely not. Around the 0.11, we might have taken the point beforehand and then used the point at 1,1, or use the point here. These are all going to be reasonable approximations. It's just convenient to pick one and use it. We would get slightly different values because we're doing an approximation to the exact derivative calculation. But anything that uses points around the 0.11 would be a reasonable estimate of the derivative calculation. The key thing is to keep the x as the variable if we're taking the x derivative, or change y only and not x if we're finding the y derivative. Well, what does this tell us? If we had our function and we found the x derivative was approximately minus 14 and the y derivative was approximately 25.8, that would tell us that as we move away, actually as we move in increasing x away from the 0.11, so that's where the reference point comes in. As we increase x away from 1,1, f increases at approximately, actually f decreases because the derivative was negative. F decreases at approximately 14 units per unit increase in x. without actual units in the scenario, that's the best way we can capture that statement. Likewise, as we move in increasing y direction, away from the 0.11 again though, then f increases at a rate of approximately 25.8 units in f per unit of y motion. And that's it. That captures our partial derivatives, and it's something that we can then estimate from data if we don't have the access to the exact formulas for our function. And it all ties back to what we mean by slopes being represented by derivatives.